Estimados colegas, es un placer para mí presentarles al doctor Nikita Mergelov. Es investigador del Instituto de Geografía de la Academia de Ciencias Rusa. En un pasado lejano, nosotros estudiamos en la misma universidad, en la misma facultad de edafología, de la ciencia del suelo, en la Universidad Lomonosov de Moscú. Él terminó sus estudios allá en el año 2002 y luego, entonces, su trayecto de la vida lo llevó a ambientes extremos, a las zonas polares frías. Hizo su doctorado con edafólogo muy famoso, doctor Víctor Targulian, que también es mi mentor. Y con doctor Sergei Goryachkin en el Instituto de Geografía sobre los suelos de la zona subártica de noreste de Rusia. Y con eso ya llegó a unos ambientes más extremos y su posterior vida académica pasó en las islas árticas. Varias veces visitó Antártida para estudiar suelos de ambientes extremos y sobre todo suelos endolíticos desarrollados sobre las superficies rocosas. Y yo pienso que por un lado este tema es interesante para nosotros para ampliar nuestros horizontes científicos, para ver ambientes que tal vez, bien, algunos colegas van a lograr ver estos maravillosos paisajes, pero mayoría tal vez no. Pero por otro lado, yo pienso que este tema tiene varias aplicaciones a lo que estamos haciendo nosotros. Desde un modelo para biosfera, y también suelos y procesos pedogenéticos y procesos superficiales en las etapas tempranas de evolución de la Tierra, cuando todavía existían solamente microorganismos y tal vez la mayor parte de la superficie terrestre fue cubierta con este tipo de objetos. Esos suelos endolíticos que ahora sobreviven en la Tierra solamente en paisajes extremos. Y hasta estudios de pedogénesis en paisajes tecnogénicos, porque los humanos están produciendo muchas superficies rocosas nuevas. Todos edificios, paisajes urbanos, paisajes mineros que estamos estudiando, todo eso prácticamente implica formación de unos objetos muy parecidos a lo que está estudiando Nikita. Él se profundizó mucho en este tema, entonces con mucho gusto le paso la palabra para su presentación.
Muchas gracias for this great introduction, and sorry I'll be talking in English, and it's really a great honor and also a pleasure for me to be here. This week we had already a couple of seminars, practical classes with students, and today is the final talk that will summarize and focus on some things that we have been discussing this week in the Institute. So, welcome to the polar regions, to Antarctica. And of course, if we ask the question whether this geological heaven is lifeless area, we'll get the definite answer, no. At least bacteria are everywhere, even in the deep biosphere and also in the superficial layers on the rocks. But if we try to think, is there some kind of place for primary production and soil formation on rocks, not just on sediments, where the soils in Antarctica are well studied, for example, by James Bocquet. Several books have been published on soils of Antarctica. But if we think about the rocks, the most initial stages of pathogenesis, how soils are starting to form from the rock. We'll try to find the answer today. So if we look at many rocks, gneisses, granites, sandstones, which contain translucent minerals like quartz and feldspars in Antarctica, we'll find that they often do not have epilithic biota. Sometimes they have, but often do not, but have something inside, the life inside, the rocks. So you see here, we just detached the exfoliation plate and find the whole botanical garden of microbiota inside the rock. And you can find this in different ice-free areas of Antarctica. This is different oases in Antarctica, the exposures of rocks surrounded by ice. And you see biota is living inside the rocks because of the stress from ultraviolet radiation on the surface, often lack of knowledge or lack of moisture, sorry, and other stressful environments that are present on the surface. So what are the conditions in ice-free areas of East Antarctica, which are very different, for example, from Antarctica Peninsula and Subantarctica? The most important here, you see the temperatures are not so harsh, and of course the surfaces of rocks and even the air gets positive temperatures in summer, and the surface of rocks can be heated up to 30, even 40 degrees due to insolation. But the winds are strong and they often abrade the surfaces, and there is no liquid precipitation, which is very important. So you have the snow cover, which is redistributed into snow patches, and then from that snow patches you have the meltwater redistributed, for example, and no vascular vegetation. Vascular vegetation is present in Subantarctica and Antarctica Peninsula, but here no vascular species. And of course also the time factor is very important. So the biota, which has a very short life cycle, like life by an hour, petagenesis by an hour, survives here, but not the flowering plants, which needs a lot of time to complete the life cycle. That's also the reason for the absence of vascular plants. And where is this important? So we have this kind of a nature reserve without vascular plants, root systems, which are most powerful agents of petagenesis as we know the soil formation today. And these extreme conditions, they switch off this vascular vegetation, and we have kind of a window into the past before the vascular plants appeared around 400 million years ago, into whole more than probably 3 billion years in the past, when soils were shaped by microbial communities. And of course, there is a great set of studies on paleosols, early Precambrian paleosols, especially from Gregory Retallack, Holland, Rye, and other paleopedologists. But they are mostly very thick weathering profiles, which have signs of organic matter, and they mostly originate from depressions, accumulative positions, and the whole record on the initial stages of petagenesis on rocks in arid regions, it is mostly erased and is not conserved in geological record. That is common for all paleosciences. That information comes usually from accumulative positions. So how can we approximate these initial stages of petagenesis? We can use contemporary modern ecosystems like those we have in East Antarctica to try to model how these first soils looked at the Earth. And currently there is a lot of knowledge collected that even in the Archean, before the great oxidation event, when the concentration of oxygen within several millions of years raised to higher levels in the atmosphere, concentration of free molecular oxygen. There were some whiffs or oxygen oases, and it is well written in different geochemical indicators, in the microbial mats, sedimentary structures, signs of oxidative weathering connected with anomalies of cerium, enhancements of uranium, manganese retentions, chromium fractionations, and so on and so on, and also Paleosols records. So we also understand that in the Archean, the ozone layer was not still formed. So the UV radiation on the surface would be sterilizing, right? So these cryptic niches, cryptic habitats, inside the rocks, they can provide protection from ultraviolet radiation. And we can use these endolithic, and also I will show you hyperlithic varieties of protosoils as the model of soil formation. When the atmosphere was low in ozone content, there was high level of UV radiation. And there are works showing that even after around 22 months exposure in the space, used under the surface, protected by minerals, the bacteria are surviving, and these are signals from carotenoids. So these minerals, they protect life from the harmful UVB, UVC radiation. And important to understand that in the rock, a few millimeters under the surface, we have, this is the day sunlight spectra, but here we see that it is highly attenuated, and mostly the red part of a spectra penetrates, the transmission of it is much higher inside the rock. And so, for example, such ancient model as chlorophyll, it has, as you know, the second peak here in the red part of the spectra, which absorbs light and makes primary production possible. So this is very important as well. So we can look at these nice features, cryptic protosoils in the Antarctica rocks, and there are several of them, indolithic protosoils as we call them, those profiles that are established inside the hard rocks, but also under the stone pavements in loose sediments where you have, for example, cyanobacteria layers, green layers under the surface protected by stone pavements. And cyanobacterial biofilms are important components of these cryptic but continuous subsurface organic layers. So to be clear, of course, endolithic systems were known for more than a century, and mostly fundamental basis for their studies was provided by Imre Friedman in the 70s. He started to study endolithic systems in the Negev desert in Israel and then in Antarctica. So this is well-known phenomena for biologists, and you have the whole microsystem inside the rock, which is fueled by cyanobacteria, green algae, fungi, lichens, so on. Nowadays, of course, this ecosystem is much more complex than in the past. And these endolithic systems and associated endolithic protosoils are widespread around the globe. This is example from Novaya Zemlya archipelago in high Arctic. And this is example, for example, from Altiplano, the high latitude part of the Atacama Desert. And when on ignimbrites, you have also cyanobacteria, endolitic cyanobacteria layers. And there are mainly two types if we look at the vertical profiles of these protosoils, two types of them, accumulative one and the one that has these white leached and iron stained red layers. So kind of a alluvial differentiation that we know also for soils. So this is a close view of this profile of the interlithic protosoil. And it's really quite complex. So we have the upper layer with rock, maybe with rock varnish on the top, different coatings, and we have this bioreactor inside, fueled by fine earth, organomineral coatings, biofilms, tissue networks. And that's how, under the reflected light, just under the stereo microscope, looks this endolithic organogenic horizon. You see a lot of aggregation of the fine earth that was produced inside the rock, not only by biological processes, but also by physical disintegration, which is present in Antarctica. And you see also signs of degradation, for example, of quartz here, like a ton of quartz, and it's all covered by cyanobacterial biofilm. And this is the cyanobacterial biofilm inside the rock. So it's a classical view of the biofilm. You see cells which are embedded in the extracellular polymeric substance. That's the view from the scanning electron microscope. And lots of such biofilms inside the rocks. And here, for example, you see the feldspar grain, which is covered by organomineral coating, which contains cyanobacteria cells. And some parts on thick coatings where you do not receive this signal from the mineral background. This coating is, we checked, about 30 microns thick. So some parts are enriched in mineral elements. So it's kind of a biomineralization happening here. And of course, we should ask ourselves a question: what is the composition of organic matter inside this rock? And if you do nuclear magnetic resonance on 13C, just to understand the functional groups of organic matter, you'll see some picture that you would expect. Not really much aromatic organic matter, just from few percents to 10%, but a lot of aliphatic structures substituted with oxygen, nitrogen. You have some carboxylation. So something in composition of organic matter that we would expect from biofilms. And also we did here Raman spectroscopy. It's just shortly to explain. You excite the molecules with laser. They are vibrating, so the energy of the laser, of the source of photons is changing, the energy, the frequency, the wavelengths, and it is different from the initial source. So we can detect this shift in the frequency, for example, which will correspond to certain bonds vibrations. And you see here a lot of different spectra from carotenoids. Some of them belong to famous beta-carotene, but also you see that there is a diversity in the molecular structure of positions corresponding to different bonds between carbon atoms. So it's a variety of it's actually a variety of different polyions, of different carotenoids that are present here. And so we expect that the organic matter is rather fresh and of microbial origin. But when we did 14C amplified mass spectrometry and also integrated it with the literature data, so we see that, like in usual soils, there are at least two pools of organic matter. The young one, which is of microbial origin, and also the old one, maybe even some of it of a few thousand years. So how could it be? So whether the settings in Antarctica are so harsh that organic matter is not decomposing, or maybe it's stabilized on something. So to go far in details, we used such method as nanoscale secondary ion mass spectrometry, which is when you bombard your sample with a primary ion beam, for example of cesium, and you get the ionization of the matter of your sample with a very high spatial resolution of 50 nanometers, okay? And you get the signal in ions. So this method is both sensitive to organic matter and to minerals. And we see that there is an organic matter sorption story on minerals here. For example, here we see the organic matter, nitrogen and carbon, which is partly colocalized with the aluminum species, so which are here proxies for clays. The process of absorption of organic matter on clays is widespread in soils. And this is a composite image of aluminum species standing for clays and organic matter. So these two compounds are partially colocalized. And this is also a scanning electron microscope image, which for this particular part we also made a nanosims measurement. And we see how green parts of carbon are interrelated to the fine fraction of minerals, mostly clays, and the peaks standing for organic matter and for mineral material are very, very close if we do a horizontal profile here. And mostly half of the aluminum species are correlated with organic matter. And also there is a sorption of organic matter species on iron-containing compounds, which are also colocalized. You see here organic matter, you see here iron, and decoupled from the silicate signal. So we know that iron oxyhydroxides are also good stabilizers for organic matter. Stabilization of organic matter means that it is partially, for some time, is not the part of the quick biochemical cycle. And there is also a story concerning the biodeterioration of the rock. You see that biofilm of cyanobacteria produces these etching pits inside feldspars. We see some amorphization at the contact of biofilm and the minerals. And we see that this organic matter is located in these etching pits, producing probably the dissolution of the rock. Okay. So actually all these processes can be seen in applying more simple techniques. In thin sections, this is reflected light, and we see biotite, which is partially substituted by biomass of cyanobacteria. And this image shows you the cyanobacteria biofilm, which is surrounded by halo of weathering. You can see here a lot of reflection from the mineral surfaces. And of course, we all know that microorganisms produce acids which are very conductive to weathering, but also cyanobacteria during the photosynthesis rises pH locally dramatically up to 9 degrees. Oh, sorry, to 9 pH to 9. So you see here the CO2 consumption. It's indicated in the photosynthesis, and pH rises dramatically. So this process is conductive to weathering of quartz. But this happens shortly and very locally. So cyanobacteria biofilm changes the local geochemical environment dramatically. And this is the image from the X-ray microtomography of the Indolithic protosoil. And you see how much weathering is produced inside. You see these bright cellular dotted regions with some signs of iron hydroxides here. And we see biodeterioration here, we see fissures, cracks produced inside the rock. And what is important for soil formation, we see the fine earth production. The fine earth production in the pores, and fine earth is the basis of the soil. This is also an example that here we see the regions of weathering and the presence of iron, which comes from the primary minerals and precipitate as iron hydroxides. And also we see this in the images under just reflected light, the connections of cyanobacteria areas with iron species. And actually, like in a podzol, we see in the rock, which is weathered and contains fissures and cracks, we see that the grains of primary minerals are surrounded by these iron-containing components. And probably this network is conducive for differentiation of this protosoil inside the hard rock, which is not sealed. It is permeable for energy and elements. And this is maybe the most beautiful example of how this differentiation is produced. This is sandstone, which was originally cemented by iron. And then here you have the leached layer, the white layer, and redistribution of iron downwards, maybe also upwards. So this looks really like something reminding us of a podzol, but with a very small profile. And indeed, these phenomena is possible not only on sandstone, for example, on gneiss. You see these bleached layers, differentiation in iron hydroxides, which produces this kind of a BS and BHS horizons that we know from podzols. The horizons connected with accumulation of iron and horizons which are leached in iron. And that's how the surface in the E horizon, in the leached white horizon, looks like. Of course, it's not just produced only by chemical weathering. Likely some frost action was present here, but the surface is clear in E horizon. And if we go to the BS or BSH horizon, where the iron and organic matter is accumulating, we always get these coatings. So we don't almost never see the clean surfaces of primary minerals. And if we do some elemental analysis by energy dispersive spectroscopy, we see that iron is colocalized with, iron is red and carbon is green with carbon. And this is a kind of a mineralogical profile. The data is coming from Raman spectroscopy. So we see this micropodzol on the rock, and the top of it is this layer contains hematite and goethite, so oxide and hydroxide. Then you get some organic matter, polyenes, beta-carotene. You can get also some carbonates here, aragonite, in this particular case, gypsum, also calcium oxalate, wavellite. And then when you go to the E horizon, the white one, you see just signal from orthoclase, quartz, other feldspars. And then in these lower BSH horizon, you have again hematite and you have carotenoid, which are colocalized in 1 cubic micrometer. So altogether, these processes produce this very bright pattern on the rocks, which, if they are not metamorphosized for high degree, it can be conserved probably in the geological record, and then if we know what to search for, can be found probably by some geochemical indices. So the earliest record of real podzol we know from several hundred millions years ago. But this approximation of that we do with the basis on the knowledge from modern extreme environments probably can extend this record far into the past. What are the products of endolithic protosoils we find? As I have shown briefly, some carbonates. So this example from East Antarctica, this high Arctic, Novaya Zemlya. So this conglomerate contains carbons originally, and we see, carbonates originally. And we see the association of carbonates with cyanobacteria. But here is an example from gneiss. Gneisses normally do not contain carbonates, but they do contain, in this case, because of cryogenic processes which can concentrate locally carbonates, because of the impolarization of salts, and maybe also because cyanobacteria are known to stabilize atmospheric CO2 in a form of carbonate if there is enough calcium from weathering inside the rock, or for example from feldspar. And here on gneisses we see a lot of carbonates and cyanobacteria biofilms inside the organogenic horizon of this endolithic protosoil. This is how they look under just reflected light. With this scale is 20 microns here. So carbonates are very closely associated with cells of cyanobacteria, so on. And the isotopic, stable carbon isotopic signature is quite biogenic here for carbonates when we removed all the organics. So this is signature of carbonates, not the biofilm produced by cyanobacteria. And indeed, when we do Raman spectroscopy, we see that the carbonates, there are different signatures from carbonates. Actually, it's kind of a carbonate continuum from most stable forms like calcite, but also aragonite, and they have different optical properties. And aragonite actually acts like optical fiber known to be present in mollusk shells to transform light into the symbiotic bacteria living inside the mollusk shells. So maybe, we don't know, but aragonite also plays this role here. It's a question that should be investigated in the future. And also we see here is andesine. It contains from 30 to 50% of anartite, according to the database. And anartite contains some calcium. And here is the cyanobacteria biofilm, and we see the signal from cyanobacteria from carotenoids, the pigments. And we see also here an aragonite. We don't know. We don't state that this aragonite was produced by cyanobacteria, and also weathering of the feldspar and combination of calcium and CO2, but these species are colocalized. And actually, if we then look at different endolithic protosoils, like at Novaya Zemlya and also in East Antarctica on gneisses, here is East Antarctica spectrum, we see also a continuum from calcite to aragonite, and aragonite is known to be a less stable crystal polymorphic modification of calcium carbonate. So it can gradually transform back to calcite. And some intermediate spectra, they are not really fitting nor calcite nor aragonite. So it's kind of maybe some transitions between these polymorphic modifications. So there is a carbonate continuum present in endolithic protosoil. And going already close to the conclusions, we can say that the rock surfaces of weathered rocks uncovered by vegetation and biofilms, containing biofilms inside, they are permeable, right, to energies, to the flows of energy, to the flows of elements. They have some residual products of interactions between biota and minerals, which are here deposited in the form of biofilm, in the form of organomineral films, some crystals of secondary minerals. So all this legacy, geochemical legacy that is produced on the rocks then can be transferred to the accumulative positions. And in case of very poor depopulated landscapes like we have in East Antarctica, they can enhance the geochemistry of the landscape. And also there are some works showing by combining several isotopic signatures that there is a real input of organic matter from here to here. So if we look at a very evolutionary perspective, we can see that the role of these initial stages of petagenesis under endolithic protosoils, when the environment was too harsh on the surface, it could be significant in enhancing the geochemistry, the complexity of the landscape. And once biota pass through the different evolutionary stage, and the fungi, lichens appeared, which are very well-known agents of petagenesis on rocks. So the complexity could have risen, the profiles can have been changed, but this is a very important line of evolution of life and its co-evolution together with petagenesis. So to conclude, we see the evidence that these endolithic systems really have many features that are common to soils. So it's the rock layer exposed to external abiogenic factors. Rock layer is inhabited by living organisms which are synthesizing organic matter and decomposing organic matter. So the initial parent rock is transformed in situ by biogenic and abiogenic factors, and the products of this transformation are partially retained inside the rock and producing the very important feature of soil, the vertical heterogeneity, the microprofile. And different layers of endolithic protosoils are connected with each other by the fissure network. So we don't look at this weathered subaerial segment of rocks as a completely sealed one. And the most common feature is that organogenic horizon is located not on the surface, but under the surface. And also production of fine earth is possible here, and different residual organomineral coatings are left here. Although macro horizons are not forming, because it's kind of a self-destructive process, the more you weather, even with the help of biota, this eternal layer, so the less cohesive it becomes. So the part of the soil is destroyed, and the gravity removes it from the rock. So this presentation would not be possible with contribution of my colleagues, which help I acknowledge very much. And muchas gracias por su atención.
Nikita, many thanks for this presentation. You really opened to us a new world of fantastic objects, and it raises, I think, a lot of new ideas, a lot of questions also. So please, we start the session of questions.
Yes, Nikita, thanks for your presentation. It's amazing, this topic. I really want to see these protosoils or soils in Antarctica. I have small doubts about how you sample these protosoils or soils in Antarctica. You identified in the field these rocks with the hole and the cyanobacteria mat, and you collected this type of sample. And the other question is how you managed to collect the sample and transport the samples to the lab. You use some special method or something like that? Okay.
Thank you. Thank you very much for the question. Well, several approaches were applied. First of all, when we first came in Antarctica, we just took these exfoliation plates. Next time, we brought the, drilling tool, a drill, circular drill, and we took the cores from the rocks to have these samples in the whole volume and to get the profiles. And then we also put these samples in the fridge, and we have a large ship from the Russian Antarctic expedition that goes from St. Petersburg to Antarctica and that backwards. So actually, you can take as much samples and as large samples as you want. Yeah. So we sometimes we just took boulders, sometimes cores, some samples for microbiology, which was not shown here. So, and then in the lab, for example, if you use X-ray microtomography, you just make an additional small core with like 1 centimeter in diameter, put it in the tomographer. You can do thin sections or whatever. That.
Thank you.
I think this is exactly what you need for your
Yeah. Yeah.
a ship which will go to program from there to make Veracruz.
Why not? But I'm thinking about the logistic of this. If I want to sample this type of soils, I don't know. I need to manage.
More questions?
Thank you. Well, congratulations for the talk. I think it was amazing the way you presented the materials. I was frankly surprised by the quality of the images. My question is more like a curiosity. I am not a specialist in soils, but from this talk, I am a little bit more clear now how the soils as a matrix appear in the history of Earth. No? And I learned also mechanisms of production of minerals and organic matter in this matrix because of these processes of endolytic organisms. But in my understanding, the soil as a matrix, it has to have one fundamental condition, which is the retention of water. And my question is, in which moment and what is the process on which these protosoils happen to have this condition of retained water to explode to all these variations of soils as we know these days?
Thank you very much for the question. So it's about retention of the water or migration of the water, more retention.
I mean retention.
Retention. Okay, so to retain something, you need first of all for water to come there, right? So it comes from sporadic snowfalls on the rocks, for example, and some water just penetrates through pores, but usually pores and fissures, they turn to be hydrophobic, you know. So it can be, and sometimes they are hydrophilic, so it's a very uneven pattern. And also the organisms have the possibility to absorb water, especially many subaerial biofilms. They have extracellular polymeric substances, extracellular polymers, which have a great sorption capacity for water. They expand and so on. So at the rare periods when the water is available, but also from not just from snow, but maybe dew and so on, depending on the location, if we are not talking just about Antarctica. So this water is retained due to the high sorption capacity of the polymers produced by biota. And I think that's the main mechanisms that stay behind that.
Okay, thank you. Yeah, I mean, my curiosity arose because in these extreme climates or environments you are describing, shall we dance? We can dance if you want. Okay. I see a lot of water, but water trapped in ice. In reality, what I imagine is the rocky systems are dry, no?
Yeah, there is a kind of, I think, of a confusion. Biologists say that Antarctica and high Arctic, it's Arctic or polar desert. But in most cases, it's not a real desert in terms of geography, because the soils are usually fueled with water at the accumulative positions. It's just, and sometimes the water that is standing over the permafrost table is not available, for example, for the upper layers. But you can see a lot of water in the soils if you go just here in these sides. Also, meltwater is coming. And of course, you're absolutely right that here are much more arid conditions on the rocks. But still, the snow comes here, yeah? And the temperature of a rock, for example, during Sunday, it rises to several tenths of degrees. So it's melting, and some input of water is coming into the rock. And then it is used effectively. All you have, biota should live there. So, and water availability is the main limiting factor, actually, for life, not the temperature. Negative temperature, I can also, even photosynthesis in some lichens is possible due to protein protection under negative temperatures. But if you don't have water at all, then life is impossible. So if life is present in these rocks, then it's still very effective use by biota of very small amounts that come to the rock. So biotically mediated process, as I see it.
Thank you so much.
Большое спасибо, вы работаете очень интересно. I have only one question. If I understood well, one of the purposes of your research is to try to apply this research in other times to see if we can see this kind of process in the past. But apparently one of the two things that could be used as a proxy is, one is the aragonite, and the other is all the kinds of biofilms that are generated as a coats. But since it's more or less easy that they will disappear and will not be well preserved in their record, so how you expect to deal with these things when you are searching in the past?
So you said two things. What was the first thing?
The aragonite.
Which one?
Aragonite.
Aragonite.
Yeah.
Okay. And the second one?
The biofilms.
Biofilms. Okay. So, yeah, during time, aragonite would likely turn into calcite, right? Or even disappear. And the biofilms, they most likely disappear, but there are some nice examples, for example, from Moody's group at the Barberton in South Africa. It's Transcaval Craton, where microbial moths preserved from 3.2 Ga from and they were formed in heterogeneous sediments, not stromatolites, right? Martin Homan and Christopher Hubick, a lot of done work about that in South Africa. So, but here we do not, of course, rely on the conservation of the whole biology and whole geochemistry. We will look into some geochemical legacy that can be left. And one of that is probably these weathering patterns, these leached layers and more iron-stained layers, and they are not very local, as I have shown you. I don't know, it will be a long way to go, I think, backwards. But they are here. They are spatially, so this, you see the geological hammer, and actually it's the whole exposure looking like that. So if it is buried and then you have a geological profile, it's likely that something of these, very solid and not obligatory containing biofilms and organic carbon, can be preserved. So the paleo people should be aware that such signatures can indicate those processes I was talking about. Did I fully answer your question, or please ask?
Yes, I think so. I just was wondering about if this can be also used as some kind of proxy for climatic purposes, for example, because for me it's a very interesting feature and very recognizable. So, yeah, thank you.
Thank you.
More questions? Más preguntas? Well, then I have some also. Of course, I have a lot of things to ask, but in this occasion, I will go to some mineralogical findings that you made. And first question goes again to aragonite, which already was asked by Haidar. I was really surprised to see this rather large-scale aragonite neoformation in this context. And my surprise comes mostly from the fact that usually in the normal pedogenesis, normal soil development and normal neoformation of carbonates in soil environments, we don't find aragonite. You also mentioned that mostly calcite is formed as a more stable species. And even we use, for example, DICE use the ratio of calcite to aragonite in neoformed carbonates to check how much carbonates are neoformed and how much carbonates are still inherited from the parent rock, which sometimes has aragonite as the rest of shells, of fossil shells. Suddenly here, aragonite appears in big quantities. What could be the mechanism behind? Why it manages to synthesize it here?
Well, first answer is that have you used Raman spectroscopy to differentiate between polymorphs?
Have you used Raman spectroscopy to differentiate?
So, oh, okay. That is fine as well. Yeah, X-ray diffraction would be suitable, of course, and it's the golden standard. Okay, then the other, for example, if we talk about gneiss, which is not the type of rock where we would expect any carbonate. Yeah. So we thought of that. So several sources are possible. First of all, it's cryogenic formation of so, for example, you have glaciation and the process called regelation. It means that you, first of all, induce the pressure of the glacier. And you have this water film between the rock and the glacier. And you have the pressure, you have the exposed surfaces of feldspars, and you have CO2 also dissolved in this thin water films. And they interact with each other And there are works, many works actually for periglacial environments, showing that under these processes, which is just a part of the cryogenic formation of carbonates, aragonite is formed. So one source of aragonite can be those inherited from the glacial stage here in Antarctica oasis. And it was just present in the top of the weathered part of the bedrock. And then cyanobacteria are using it because cyanobacteria can rely on CO2 from atmosphere, but also on carbonate CO2 as well. But something is more complex happening here. As I have shown, it's not just two. Well, usually we have the other end member is veterite if we are talking about the crystal polymorphic modifications, calcite and veterite. No veterite here. But between these two members, there is a variety of signatures which we can see here in these parts of the spectra. Some of them are kind of corresponding to the cryptocrystalline forms or amorphous forms of carbonates. So we see the signs of transformation here. And the other process known by cyanobacteria, calcite precipitation, very well known for aquatic sediments during photosynthesis, right? Self-biomineralization. That produces only calcite. So, and there is a continuum of this. So, and probably other processes that stand here behind these aragonite phenomena.
Very, very interesting considerations, especially this cryogenic aragonite formation, because exactly aragonite needs higher pressures.
But you don't have high pressures in mollusk shell.
Of course not.
Yeah.
Somehow life is
can
able
do it
to
without
overcome.
pressure.
Yes, life can do it without pressure. Great. And the other question is related to the iron oxide mineralogical species. In the podzol, in this nice podzol with reddish alluvial horizon. I was surprised, well, of course, I was surprised to see in this podzol in some levels aragonite and gypsum, which are practically forbidden for normal podzol, which is acid, very acid soil. So this is not exactly podzol, of course. But what my question mostly is that the dominant and supposedly neo-formed iron oxide here is hematite. We are accustomed that hematite, red-colored iron oxide, is mostly a product of more advanced weathering in subtropical and tropical areas where the soils are red, as some soils in Yucatan Peninsula. But in the temperate and cold environments, we usually see goethite and other hydrated iron oxides and not hematite formation. On the contrary, hematite, when inherited, is transformed to goethite, and suddenly here it is neo-formed. What is the reason?
First of all, it's not obligatory neo-formed. You actually, on the top of the rock, you have a weathering rind, and which contains hematite. And it's also concerned with the question of the water availability. So these conditions are quite conducive to oxidative processes. So the weathering of the bedrock without biota would produce the weathering rind with hematite. You have a shortage of water, please remember, on the surface of bedrock. And then, while biologically mediated, it can be transformed to goethite. So it's opposite situation. And we have oxidative conditions here. And biota leads to this differentiation and production of leached horizon in the weathering rind, which was already fueled, for example, by hematite, by other processes. Okay?
Yes, but alluvial horizon
Yeah,
Full of hematite.
yeah, it's just moved here. And also it has a connection to carotenoid. So it can be kind of a more complex kind of mineral transport here. So yeah, and goethite is, at least in this case, we found at the top.
Still, I feel that some question is behind this, still unsolved, maybe. Hematite of the extreme environments. Sounds really strange. Mhm.
Oh, it's if you take the weather, all these red rocks here, for example. Okay, no, that way. They are full. Maybe this one. These red parts here, weather, they're full of hematite.
They're full of hematite.
Hematite without biota, just stay.
Mhm.
Yeah, and especially to be careful in our conclusions, we used very low power of laser because and very long exposure at low power, because if you use higher power of laser, you will always get hematite, because it will be any iron oxide, hydroxide will be oxidized to hematite, right?
In the course of analysis.
In the course of analysis. So you should be very, very accurate here, but we were. So, and it's common. The sandstones in McMurdo valleys in in Antarctica, Beacon sandstone, famous one. It also has a cement of quartz grains by hematite.
Inherited hematite.
Inherited hematite.
Mhm. Thank you so much. I think we have, we will follow with this discussion already later in the different meetings which we'll still have with the colleagues. And now I think if there are no more questions or comments, we finish this event. We thank again Dr. Nikita Mergelov for his talk, and this is your diploma.
Muchas gracias. Yeah. Thank you. Thank you.